Okay, let's look at the application of the radioactivity section. We're going to look at PET scanners or positron emission tomography scanners, and this is all based on the fact that positrons, antimatter, like this here, which is the opposite electron, when it strikes an electron at the right speed there, you get annihilation occurring. Now that means they basically destroy each other completely in terms of the mass. So they both disappear and their mass becomes energy by E equals mc squared. That mass gets converted to energy in the form of gamma rays, and so you get two equal gamma ray photons going in opposite directions here to conserve the total momentum, okay? Because it's approximately zero and these approach each other and annihilate. Okay, so the total momentum beforehand is roughly zero. To be zero afterwards, you get a pair production there of photons, and they're equal and opposite to keep the total momentum zero. So this is going to be used in this positron emission tomography. So let's have this look at how this works. Now, positron emitters are not natural, okay, so we normally have to make them by putting them into a cyclotron, some sort of sample, and we actually fire protons at high energy so they overcome the repulsive force, get close enough to cause a nuclear reaction, and we make them in a cyclotron. We used to do that in Melbourne here in the Austin Hospital, and they have that shipped over for us to use here in our PET scanners. Typical ones we actually use here is you actually produce fluorine 18-9 in a cyclotron over there and ship it over here, or sorry, fly it over, because that'd be quick. Now that there has too many protons. It's one of those unusual ones that actually needs 19 as a total mass number to be stable. So that will actually decay by releasing that positron to reduce the positive charge, to reduce the number of protons in there. So it has too many protons. So this will then naturally decay in the body as part of a chemical. So the one we were using for in Adelaide was to use deoxyfluoroglucose, and that fluorine was radioactive, formed in the cyclotron, chemically reacted together and sent over here. And you inject this into the body. And what it's going to do here is the fluorine is going to decay by releasing the positron. That's why it's a positron emitter, positron emission tomography, and you'll balance the equation with 18 and 8. It changes into oxygen in that process. So this is the positron that's formed, and that's the key part. So let's just have a look at that here. So what's going to happen here, in this case we're going to get the fluorine in the deoxyfluoroglucose decaying naturally, because it has too many protons, into a neutron and releasing a positron here. And that positron will be slow moving and collide with an electron in one of the atoms. So when it does that then, it does the annihilation and you get gamma ray production in opposite directions here as shown, going off to some detectors. This is what one will look like. What you can see here is you've got the ring of detectors there, the patient goes inside there, and they're injected with that deoxyfluoroglucose. And that's to check the metabolism of the heart. You can also use a oxygen labeled one, which is high in protons, which is attached to water chemically, and that's injected and follows the bloodstream around and sort of monitors oxygen flow around the blood. So what's going to happen here is when the photons go out as a pair from a particular place in the patient's body, they're going to go out and form a coincident line. They're going to form a coincident line there and go to two opposite sides of the ring here, be picked up by the scintillator crystals, go through photomultipliers to increase the number of photons, and then be sent off to a computer. And obviously they can time how the delay between this one arriving and that one arriving and work out the different distances there from these two parts of the ring to the object where they're actually emitting the photons and work out its exact location. They don't use one coincident line, they actually use pairs of coincident lines like that, and where they match then and overlap, that's where they'll actually sort of pick that out as identifying it as coming from here as a hot spot of lots of fluorine being used. In this particular one, we're using the deoxyfluoroglucose because that's actually glucose as a sugar, which is going to be used by the muscles that are actually active when the patient's lying down. And one of the most active organs is going to be the heart because that's going to be pumping away. So you can actually see what the metabolism of the heart's doing with the deoxyfluoroglucose. But the oxygen is used in labelled water to measure the blood flow and the oxygen use around the body. Okay, so there's two different uses for these different ones. This just shows you the photomultiplier, the scintillator crystals there, and the ring of detectors there. And this is a typical picture of one. And here's another one, just showing you there. And if you compare a CT scan with a PET scan, you can see the difference in detail of what's being given out here, what the hotspots are doing there in the liver, as opposed to what a CT scan would show. So you normally get more information out of this PET scan. Let's just look at this a bit more slowly. So in terms of the course here, you need to be aware first of all that certain isotopes will become concentrated in certain tissues. So in the case of the heart, the deoxyfluoroglucose is being mostly used by that part because the rest of the body is not very active. So this is where it's going to concentrate itself, the glucose there, the sugar. All right. In the case of the oxygen that's labelled, it's going to go into the blood and follow the bloodstream. So that's the first point. Be aware that it's concentrated in certain tissues. In the case of the fluorine here, we're saying it's attached to deoxyfluoroglucose. All right, and that's going to go into the heart there. When the radioisotopes such as these decay, then with their rich in protons, they're going to release a positron. So this is its decay at the moment. It's going to release a positron plus a neutrino. That positron is going to interact with an electron in an atom nearby within 1 millimetre, doing annihilation and producing 2 gamma ray photons in opposite directions with equal size. So there's the argument for that. The total momentum before is about 0 because they're slow moving when they approach each other. Then you're going to get equal momenta in opposite directions to cancel out and keep you the total momentum of 0 there for the cancelling. Now that photon pair is going to be detected by those photomultiplier tubes there with the scintillation crystals there. They're going to match up which ones are which based on going in perfectly opposite directions to particular sort of detector sections in the ring. So that ring of detectors will detect them. They'll be put together as sets of pairs, those coincident lines, all right, and they'll actually identify where that particular group came from. And the computer analysis will actually match those up and actually plot a map of that to locate the isotope for several different sections of the body, okay, all at once. So one use of the PET is the oxygen-15, used for the blood flow as a tracer, as I said, attached to water. The other one is the fluorine in deoxyfluoroglucose to measure the metabolism in the heart. So we're near the end here. So why do PET facilities need to be located near particle accelerators? Okay, many of them have short half-lives. All right, so the deoxyfluoroglucose, the oxygen, has short half-lives. I think the fluorine one is about 110 minutes. Now that means after 110 minutes, only half of the deoxyfluoroglucose is now active. The activity's gone down. You go through that period again, it's down to a quarter, then down to an eighth, then to a 16th. So in the period of 8 hours, you've really gone down to a very small fraction of activity of what you would have started with. So it's a lot harder to get that to work in the body and be useful. All right, you basically have to increase the dosage a lot to get the same amount of activity out. So that's not practical. Okay, thank you.